here and to present this scientific talk that will hinge about the novel algorithm that can be found for machine learning from the connection with topological quantum physics. I am Antonino Marciano, and I'm professor of physics at Fudan University. So probably one of the main problems of artificial intelligence and machine learning is that one of generalization. And the problem arises because of the fact that there is not a complete explainable situation for what concern deep neural networks. So this lack of explainability percolates in a lack of trust that at the end of the day we can have on the algorithms themselves. And some of the issue pass through a kind of overfitting and underfitting of the data that happens. And this is usually connected to the complexity of the sample of data and to the way the error estimates are performed. They're all intertwined. So a new paradigm somehow is required in order not to avoid overfitting and underfitting, and in order to avoid the problem issues that are driven and are provided by complexity. So recently, a new paradigm is being proposed, which has to do with, let's say, quantum neural networks. What is the point here? The point is that we assume, we associate points of a space of representation with the training data. That's what we do usually. And now, I mean, that's this point of the space of representation are encoded and are seen as representation of some quantum operator. So basically, the logical gates become quantum operators. What I will show, and this has been done in the last years, for instance, notably one of the last publications is by De Boer and other people on this subject, refining and recovering some quantum algorithms. So what I want to show here is some common work with a group of people that I will emphasize later, including Filippo Fabrocini, Enrico Greco, and Costa Tersidis. Is a common work in which we take into account the structure of a graph in order to encode the complexity of the training data and of the sampling data. So, and in this way, we have the possibility to encode more information than in the traditional machine learning, let's say, paradigm. And in this new framework, we aim at disentangling the situation of deep neural network as a limit of quantum neural network, but of some quantum neural network which are more general than the one that have been considered so far, that are the so-called topological quantum neural network that are nothing but graph. So still continuing with this paradigm of quantum neural network supported on, let's say, graph which only restrict to the nodes. So the idea is to associate some certain number of entry data to a certain number of nodes, and to associate input and output to the boundary states, and to associate dimension of the representation to dimension of the reducible representation. So then the idea of the quantumness that we're going to instantiate even more than has been done before is the fact that we have to sum over an infinite amount of trajectories. So basically it's like going from the birth to death, and I mean, it's considering all the possible paths you can have in your life, and your life in this case is a sum over all these possibilities. And here what we have to do, we have to consider all the possible intermediate hidden layer, in that in a certain architecture of AI allows to find the classifier. The quantumness in particular, in this paradigm that we're taking into account, as you can see on the left, is basically going from input layer to output layer, and the input and output data are supported now on some graph, and these graphs are colored by reducible representation that account for the information, for the, let's say, metric information. But there is also topological information. This topological information is encoded in the topology of the graph. And in going from the input layer graph to the output layer graph, now you encounter an infinite amount of hidden layers. So here there is a step which is discrete, but actually you have to sum up to infinity. So you have to consider all the possible hidden interlayer, which are quantum that constitute the series here. So this is nothing but a realization of, let's say, the double slit, but actually infinite slit experiment, in which here you have an infinite amount of filters from initial to the final position, and these filters actually are the hidden layer that provide the way to process the information, to refine the information. So this is why we expect that this algorithm is going to be somehow much more precise than the previous one, because it doesn't use only a finite amount of hidden layer, but some over infinite amount of one. And the other point that I was making before is about the metric information. So basically about this irreducible representation, that is irreducible representation of some group. So group basically is dictated by the symmetry of the system. And the symmetry of the system are represented, let's say, by the symmetry of the graph, which represent the initial and the final, let's say, data, so the final states, initial and final states. So the way it is the way it is then, I mean, as the symmetry are encoded is through reducible representation that are assigned to the links and are assigned to the nodes of the graph, which are the boundary. And then this graph evolve. And the evolution is actually through the symmetry. And this is the deterministic part, if you want, of this construction. It's deterministic because the theory from point of view of mathematics that allows an instantiate this evolution is a topological quantum field theory, which is nothing but the equivalent of any kind of generalized theory of gravity. So from an analogical point of view, we instantiate an evolution through the symmetries, and the symmetry drive indeed the dynamics. And as I was saying, the dynamics is in the bulk. Here you can see some boundary spin networks. So these are boundary states. Spin network is just the terminology that we use in the jargon for the state. And this red boundary state are the initial, for instance, on the bottom, and the final, for instance, on the top, one in the left figure. And the evolution is in the bulk. So this is a one complex, a graph that evolve in a two complex, which is done of surface faces, and these faces meet at edges. And the edges, to the edges are associated some weights that are dictated nothing but the mathematics, that is basically the symmetry of the process. This is absolutely reminiscent of what happened in physics, in which the symmetry actually is dictating the dynamic of a system. Here, the system are seen as effective system with an effective quantumness. So this is not a clear quantumness one-to-one. Is everything effective in this paradigm? And indeed, this evolution is dictated in this effective realm, in this effective point of view, from the symmetries in a quantum way, because we sum over all the quantum trajectories. So we impose this symmetry as quantum operator. So once all this machinery has been developed, we can then finally find algorithm, which are the quantum algorithm I've been talking about, that allows to have an estimate of the main parameter. So for instance, this estimate may arise through the steepest descent method, gradient descent method. So this is, I mean, we can have a wealth of methods that can be applied to disentangle the parameters that we are accounting for. So in particular, I want to show a very simple realization of the algorithm, which pertains to the case of the recognition of the letter L. So we have here images 3 times 2 with 6 pixels, and there is a way to associate the boundary state. So this graph, which are colored by reducible representation of a group, which is the group of rotation here. So is SO3 or is double covering SO2. And now what we want to recognize is the lower left figure, which is a perfect L. So it's a prototype for a perfect L. What we do is an internal product in which there is the information about the projector of the dynamics. So there is this physical internal product, which gives the amplitude of probability to go from any kind of these letters to the one that you have to recognize, so to the lower left line. And then you have amplitude of probability, and the square is basically the probability that you can recognize given one of these other figure, the L. So why we're excited about this paradigm? Well, we are excited because now we can also make contact, direct contact with topological materials. So for instance, if you take into account graphene sheets, we can indeed think that, I mean, each one of these boundary states is basically the state that capture one of the layer of graphene, and then we can stack one of the layer on top of the other, and we can have a discrete representation of these quantum histories, these sum over quantum histories, in which every graphene is a bidimensional, let's say, space section of the universe that is evolving. And as we know, I mean, it's whenever we consider this situation in which more graphene sheets are attached one to another, then, I mean, some non-trivial electronic properties arise. So this already happens for two sheets of graphene, the bilayer graphene. But if you take into account the aerogel graphene, which is on the right, you can see that there, I mean, it's this sample, which is extremely light, has inside an infinite amount, a very large amount of graphene sheets, which is randomly let's say, oriented. And usually, let's say, these graphene sheets are interconnected by bridges of polyacetylene or carboxybenzaldehyde. And because of this bridging that is realized in between the graphene sheets, we can now think of this as a multigravitational system that then we can study through the lenses of extended theory of gravity, or even draw analogies simply with the wormholes and with black hole physics. And this object, of course, must be studied in a large volume limit, and this large volume limit is the statistical limit of the system that interconnect them also to spin glasses. There is also the possibility to interconnect this possibility with another thing, which is the one of taking into account let's say, nonlinear optics. Nonlinear optics can realize some knots and links of light. It is a topological structure. This topological structure can be actually realized and shaped concretely in reality, and has been measured. And the way these knots of light behave, basically, they allow to implement and encode topological information. So they allow to develop, let's say, the same mathematics that have been showing before from the point of view of, let's say, nonlinear optics. So this is another way to realize a device that implements the same theoretical idea, and then, I mean, the device would then be constituted by, let's say, optical means. Okay, so basically, I mean, the idea is that, I mean, we can realize now quantum circuits. For instance, we can write quantum circuits in quantum computers that realize tasks even of artificial intelligence, and this is new. This is new because we can do that because of the connection with the topological quantum neural networks, which is natural here. So we can consider, for instance, a system, discrete system with a certain number of, let's say, qubits, and this is in connection with the topological quantum neural networks, and realize an amplitude, a transition, and to this transition, let's say, we associate some numbers, which are basically the probability for the transition. So this is a system that can be concretely shaped. Okay, we need coherence, so we need very low temperature, but can be concretely shaped. And now, I mean, we arrived to have a sizable number of qubits, and basically this constitutes a prototype of quantum, let's say, circuits for AI, for quantum machine learning, that is achievable, and it would be more and more achievable in the future with tasks that now can be also accounted for task of machine learning. So thank you.